There we go. All right. So section 4.2. This is on graphs of exponential functions. We will not go in extraordinarily deep here. But it is important that you kind of get the overall vibe of what our exponential functions look like, if they're growing or if they're decaying. And the other thing that's going to be really fun that we're going to bring into this is that all of those shifts and reflections and everything else that we did in section 1.5, right? Shift to the left, shift to the right, up, down, reflect, etc. That's all going to come back here and be helpful for us. But this should only take like a couple class periods for us to go through. Okay. So we want to graph a function. Let's see what our exponential functions look like. Now, it is the case that there's graphing calculators and there's all sorts of ways that you can just kind of estimate what the graph is. But whenever I start out with a new sort of function, I like to graph it by hand so that I get a true feel for what it actually looks like. So I'm going to graph 2 to the x. Now, in general, recall our exponential functions are of the form a times b to the x. In this case, our a is just 1. Okay? So let's make a little XYT table. If I plug in x equals 0, what is 2 to the 0 power? 1. If I plug in x equals 1, what is 2 to the first power? 2. If I plug in x equals 2, what is 2 squared? 4. One more. If I plug in 3, what is 2 cubed? 8, right? 2 times 2 is 4 times 2 is 8. 3 squared is 9. So
that's what I was thinking.
Yeah. Okay, I can plug in negative values. I have no domain issues here. Okay, so I can plug in negative values as well. Okay, now I'll actually write this out just to get you in the swing of it. If I plug in x equals -1, I have 2 to the negative first power. How do I make my exponent positive? You bring it down to the denominator. Remember the property of exponents, like x to the negative n is 1 over x to the n. If you forgot that property of exponents, remember it now. So this is the same as 1 over 2 to the first, or 1/2. If I plug in -2, I'm looking at 2 to the negative second power. How do I write that with a positive exponent? 1 over 2 squared. So don't we get 1 to 1/4? I could plug in -3. Then I'm looking at 2 to the negative third power, which is 1 over 2 cubed, or 1/8. What if I plugged in like -100? Wouldn't we get 2 to the negative 100 power? Isn't that 1 over 2 to the 100 power? Which is, I'm not sure, but it's a teeny, teeny, tiny number. Okay. So if I was to plot these points, notice I'm at 0, 1. When x is equal to 1, I'm at 2. When we're at 2, we're up at 4. And it keeps growing from there. And then notice at -1, I'm at -1/2, then -1/4. Oh, this is a really bad graph, but there we go. This is the basic graph of our exponential function. Now, the thing that I want to point out is as X gets really small, our Y values approach 0. But can 2 to the X ever actually be equal to 0? No. Okay, 2 raised to whatever power you put it to can never actually be 0. It gets closer and closer and closer and closer and closer to 0, but it's never actually equal to 0. So what we say is as X gets really small, our function values are approaching 0, but they never actually equal 0. We have a name for this, and we'll talk about the name later. Okay. Y'all okay on this graph? Okay. Now I'm going to show you another graph. Notice we have exponential growth here. We knew we were growing because our base is greater than 1. I'm just saying these things to try to tie all of these ideas together. Now, what if we wanted to graph y equals 1/2 to the x power? Notice here my base is between 0 and 1. And because of that, aren't we going to have exponential decay? Aren't we decreasing when our base is between 0 and 1? Now, we could plot points to make this graph, but I'm going to show you something even cuter in a moment. If I plug in 0, what is 1/2 to the 0 power? 1. If I plug in 1, what is 1/2 to the first power? 1/2. If I plug in 2, aren't I looking at 1/2 squared? What's that equal to? 1/4. Are the rest of you with me? Okay. You okay? All right, I could plug in 3. What's 1/2 cubed? Someone else. What's 1 cubed? 1. What is 2 cubed? 8. Beautiful. What if I plug in -1? Then I have 1/2 to the -1st. You may or may not recall another property of exponents that we had is if you have a fraction raised to a negative exponent, the way to make the exponent positive is to flip your fraction. So isn't this the same as 2/1 to the first power, or 2? What if I plug in -2? Then I have 1/2 to the -2nd. Isn't that the same as 2/1 squared? And what do we get? 4. Well, let's plot these values. When I'm at 1, I'm at 1/2, then 1/4, etc. If I plug in -1, then I'm up at 2. So can I show you something so cute once you have that graph drawn? Tell me when you got it. Okay, look at these graphs. This was 2 to the x, and this is 1/2 to the x. I claim that these graphs are reflections about the y-axis. Doesn't that look like it? Take this one and bebop it, and you get this one. Or take this one, bebop it, and you get this one. But do you remember from section 1.5 what it is that you do to reflect about your y-axis? If you don't remember, it's fine. Isn't that where we replace x with negative x? Check it out. If I took my 2 to the x and replaced it with negative x, can't I rewrite that as 2 to the negative 1 to the x power? Why? Because when you raise something to a power raised to another power, you multiply your exponents. And isn't 2 to the negative 1 1/2? Isn't that cute? Yeah, it is cute. So, some general things about exponential functions and our graphs. Okay, we know if b is greater than 1, we have growth. If b is between 0 and 1, we have decay. So if I take a growing one, okay, this point right here is our a value. Okay, right? Remember, a is our initial value. In other words, the value of our function when x is 0. In these previous cases, we just had a to be equal to 1 because we had 1 times 2 to the x power. Okay, what I want you to notice as follows, and notice my notation. As x gets really big, in other words, as x goes to infinity, don't our function values also fly up to infinity? See how I wrote it? As x goes to infinity, our function values go to infinity. In this graph, as x goes to negative infinity, in other words, as x gets really, really small, what do my function values approach? 0. Okay, so what I want to tell you in general about our exponential functions is that the domain of these are all reals. We have no limitations as to what we can plug in for our value of x. You can plug in any darn thing you want, positive, negative, fractional, whatever you want. Our range, notice, is 0 to infinity with a parenthesis next to our 0. Now, what this tells you also on the depressing end, when we're talking about, for example, decay, radioactive substances decay exponentially. In other words, they're never actually equal to 0, so they never fully go away. Okay, we have a vertical intercept or y-intercept. That's at A, that's our initial value. And notice this never touches or crosses our x-axis, so we say there is no horizontal intercept. What we do have is what we call a horizontal asymptote. And asymptotes are going to be a big deal in chapter 3 when we graph our rational functions. In this particular instance, our horizontal asymptote is the line y equals 0. Now, what is a horizontal asymptote? When you're talking about that sort of thing, you're talking about what we call long run behavior. In other words, what happens either as x gets really big or really small. Okay, and what we're talking about is if as x gets either really big or really small, in other words, goes to positive or negative infinity, if your function approaches some constant value, then that horizontal line, y equals that value, is your horizontal intercept. Notice here, our horizontal asymptote is y equals 0. Because as x gets really, really small, our function values approach 0. Now this, again, is for growth. What I want to say, just to spell it out a bit more, b greater than 1, we have growth. So we saw then as x goes to infinity, our function values go to infinity. And as x goes to negative infinity, our function values go to 0. That's what we just saw right here. On the other hand, if we have decay, we saw what happens with our graph there. Okay, what happened to our graph? Well, as x gets really large, aren't our function values going to 0? Zink. And as x goes to negative infinity, our function values are shooting up to positive infinity. Y'all with me? It actually might only take us today to go through these. Okay. Now, this is the main thing of what I want you to know with exponential functions. Okay. And the graphs. Now, there are more specific ways of looking at these things, and I want to talk about them. I want to do this. Okay. We can also have more complicated looking exponential functions that have been transformed. And I just kind of want to remind you of just our various shifts and transformations, etc. Okay, so if I just have this general function, okay, so f of x is 2 to the x. If I look at f of negative x, we saw that that reflects at about our y-axis. Right, so if this is my graph of 2 to the x, 2 to the negative x just reflects at about our y-axis. Negative in front of your function, what is that reflected about? That reflects it about our x-axis. And in this case, if f of x is 2 to the x, negative f of x looks like negative 2 to the x. We also saw that if we add and subtract a number after the function, we move it up and down. So for example, 2 to the x minus 1 here, doesn't this just take our general graph of 2 to the x and then we go down 1? Do you remember these kind of, sort of? And f of x plus or minus in parentheses, that goes left or right. So for example, if I have 2 to the x minus 1 power, that goes right 1 unit. Do you all see how that is what f of x minus 1 would look like? Okay, just want to be sure. Okay, so let's just play with a couple more. When we transform some graphs, and what I'm going to do is actually generalize them. And I'm going to say any transformed exponential function has the form f of x equals a times b to the power of x plus c. And I'm going to tell you two things. Y equals c is your horizontal asymptote. Okay. I write horizontal asymptote as HA because it's a lot of writing otherwise. I'll write it right here again. And in general, your vertical intercept is A plus C. And let me show you how that translates to what we just did. So if I take 2 to the x, I think you grant me, if I was to write it out in this form, I would say that's 1 times 2 to the x plus 0. Do you all agree we got this y equals 0 to be our horizontal asymptote? And my vertical intercept is A plus C. In other words, 1 plus 0 or just 0, 1. So this is as general as we can get it. And what you want to keep in mind are those two things. Oh, awesome. So what I want to do is play with some examples. In other words, given this, graph it. Given a graph, give the function. Sound exciting? I mean, about as exciting as a Monday can be. Okay. So what if I do this? Give a formula for and describe the long run behavior of, I'm actually going to draw a graph. And I'm obviously going to have to label things because my graphs are never that great. So this is the ordered pair 0, 2. Here's my ordered pair 1, 5. And that's the value of -1. So when you want to give the formula for, you need to find A, B, and C. Okay. So going back to what we just had, we saw that C was our horizontal asymptote. So will you all grant me that we have a horizontal asymptote at -1 here? And therefore C is -1. So don't we already have y equals A times B to the x minus 1? Now, what is our vertical intercept? 2. And didn't we see that when we've done these shifts up and down, our vertical intercept is A plus C? Right? Vertical intercept is A plus C. Well, we know what C is. We had C is -1. So A plus -1 or A minus 1 is equal to 2. So doesn't that give us our value of A to be 3? What do we need to find? We got to find B. Well, what is the one other piece of information we have not yet been given, that we have not yet used? This ordered pair of 1, 5. So let's plug it in. 5 is equal to 3 times b to the first power minus 1. Well, aren't we then solving 5 is equal to 3b minus 1? We can solve this. How would we do it? Add 1, so we get 6 is 3b, or b is 2. So the equation of this exponential function is 3 times 2 to the x minus 1. Isn't that cute? So essentially what we're saying is take the graph of 2 to the x, multiply it by 3, that stretches it, and then move it down 1. Let's do another one. Oops. Okay. So I'll write my ordered pairs. That ordered pair right there is 0, 5. And this ordered pair here is 1, 1. Not drawn to scale. What we want to do is write the equation of this exponential function. What do we know right from the get-go? C. What is C? Good job. That's our horizontal asymptote. We see we have a horizontal asymptote at 7, right? As x is getting really small, my function values are approaching it. All right. Well, the next thing that we have is we have our vertical intercept. Don't we know that a plus c is equal to 5? Well, we found c. What was c? 7. Therefore, what is my value of a? -2. Now notice, it makes sense that we have a negative in front of it, right? Doesn't this graph look like it was reflected? Well, now we just got to find our value of b. We've used this, so let's just use the one more ordered pair. We're going to plug in x and y both to be 7. So aren't I solving 1 is -2b plus 7? We can do this. We can subtract 7 from both sides and then divide both sides by -2. Isn't this fun? Questions there? All right. So just tell me. What does this graph look like? Okay, this +3 here tells us up 3. What does the +3 in here mean? Left 3. So this is literally taking our graph y equals 2 to the x and shifting it to the left 3 and then up 1, 2, 3. Not drawn to scale. Isn't that cute? Isn't it neat how all of these things just kind of compound? What about if I have -2 times 3 to the x plus 4? Well, first thing I would write down is what's my horizontal asymptote? Let's say that's 4. And we could just describe the graph as well. Okay. And again, we could do our vertical intercept here as well. What's our vertical intercept here? Isn't it a plus c? So -2 plus 4 or 2. But again, if we want to think of it just very loosely, we're starting with the graph of 3 to the x, which looks mysteriously like 2 to the x. Okay, if I multiply it by 2, doesn't that vertically stretch it by a factor of 2? But then the negative tells me what? Reflected about the x-axis. So we've now reflected it about the x-axis and stretched it. And now that we've done that, what does this plus 4 do? And then we shift it up 4. So again, if we've reflected it, we're at -2, and then we go up 4. Okay, now what I want to do is share my screen with all of you. Oh my. We're in 121. Go. I got to share it with the Zoom. So section 4.2, I want to show you what your online homework consists of. All right, so with this section 4.2, I love the first 2 questions the best. Okay, so what you're doing in these first 2 questions is playing match. Notice here we have some initial values of 4. Here we have an initial value of 2. I claim you can already tell which graph matches with that one, right? Because the initial value is our intercept. Okay, notice that 1, 2, 3, 4 graphs all go through the same intercept. Okay, now notice that B and O, blue and orange, are both increasing. Okay, you should be able to get that by process of elimination just by looking at the bases. Okay, because I claim that O is growing a lot faster than B is. Similarly, R and G are both decaying. So what does that tell us about our base of our exponent?
Less than 1.
They're between 0 and 1. So already we know that green and red are these 2. And notice that our red one is decaying faster than our green one. Okay, so question 1 is literally just asking about familiarity and playing match. Question number 2, here what they want to know is if these have the form a times b to the x, Which graph has the largest value for B? Well, wouldn't that be the one growing the fastest? Okay. Smallest value for B, isn't that the one decaying the most? And largest value for A, how do you determine that? The intercept. Questions 1 and 2 really dig at what I want you to get out of this, okay? The fact of the matter is we all have, Desmos graphing calculators. I mean, there's the technology to graph, okay? But what I want you to have is a feel for what these values of A and B do to your graphs. Okay, part C or question 3. This just plays with reflections, right? When you replace X with negative X, you reflect it about your y-axis when you put a negative in front about your x-axis, or you can do both. But this just plays with general reflections. Again, I think that's really just furthering what we did in section 1.5 and just relating it to these new sorts of functions. This is also another 1.5 sort of question. We're taking an exponential function, and if you shift it down 5, doesn't that mean, for example, we subtract 5 at the end? Y'all with me here? Okay, so that's another 1.5 question. This is actually a 4.1 question. Don't forget how to find the equation of an exponential function when it passes through 2 ordered pairs. Okay, that was from last section. And then we have 2 more where you're playing match. And what I would suggest you do here, first notice this is decaying. So it can't be any one of these 3, can it? No, it's got to be one of these 4. Or it can't be those 4. It's got to be one of these 4. And the best way to do it is just to look at your ordered pairs. Notice when you plug in -1, what comes out? 5. So that should really give you a hint as to which one of these the graph is. Okay. And this one is a similar one, and I'll just show you what it looks like. It's just going to literally be just one of your exponential functions shifted up or down. Okay, so I wanted to go through that because I wanted to show you what you were expected to do in this section in terms of the online homework, because I know that we just went really quickly through this section. But again, what really matters to me is that you have that general feel for these graphs. You okay? Cool. So, well, we could start the next section. Or we could just say we can wait till Wednesday if you've had enough. We can vote too. Who wants to start 4.3? Who wants to wait till Wednesday? Okay, you win. I'm the lone one. Enjoy getting out of class early, Mike.